Lia is in Turin, where she also received her PhD in 2006.
Yes.
The Politecnico University of Turin, right? And you also did your master's there.
Yeah.
And after this, Lia worked at IM3D, which is a medical imaging lab in Turin for 9 years, right? And you also have been chief scientific officer for the last 3 years there, before you eventually started with a tenure track assistant professor at the university, right?
Yes.
Yeah. And yeah, Lia is also very active in editorial boards of Frontiers in Medical Engineering or the IEEE Consumer Electronics magazine, and also senior member of IEEE and the Computer-Aided Imaging Analysis Subcommittee, right? So that reflects your strong interest in medical image analysis, right? And yeah, today we will hear about Neuro-Symbolic AI techniques and how to integrate symbolic knowledge, representation, and reasoning into deep learning. So I'm looking forward to this.
Good afternoon, everyone, or good lunch, good morning, wherever you are online. I am really grateful to Katarina and the machine learning group for this invitation. My talk today will be about recent advances in neuro-symbolic AI within the context of computer vision, because that is where my research and experience is predominantly based. But I think that most of the problems and issues that I will discuss today apply to virtually any type of data. So even if computer vision is not your cup of tea, I hope that some of the examples I will be drawing will still resonate with you. I work with the graphics and intelligent systems at the Department of Control and Computer Engineering. I'm an assistant professor. My career has been unconventional because I moved back to academia after spending a time in industry. And I do have a lot of experience in medical imaging, but most of the problems I will be talking about today are not strictly tied to the medical domain. And I'm really inspired by a set of techniques which I encountered in the late 2010s, which have been trying to put together two paradigms in AI, the connectionist or machine learning paradigm and the symbolic or knowledge representation and reasoning paradigm, which historically have been two competing paradigms. As you all know, especially with the rise of deep learning, when AlexNet won the ImageNet challenge, modern AI is really focused and has really, again, a lot of attraction and interest in deep learning. However, there are attempts of bridging these two paradigms into a coherent picture. I date them to the 2010th decade, although the concept of hybrid system is really comes from the 90s, even before. I think this is the period where most of the paradigms that we use today have emerged. Why do we want to do that? I think the main motivation can be quickly perceived if we look at the weaknesses and the strengths of statistical AI or machine learning and symbolic AI. If we look at statistical AI, we know that there are some issues, some long-standing issues related to deep learning, such as the inability to incorporate domain constraints and the sensitivity to biases and shortcuts. Statistical AI is essentially data-driven, meaning that everything we learn, whether we intentionally do it or unintentionally do it, must be embedded in the data. Which comes with data hungriness and sample inefficiency. We need huge amount of data in order to train these systems, and this problem is being exacerbated by a rush towards building larger and even larger models. We also have issues with explainability. There have been advances in explainability, but still it is quite difficult to achieve and requires some form of post-hoc, usually interpretation. And we have problems in generalization, although these type of systems can generalize extremely well within domain. We have some long-standing issues in generalization and compositionality. Whereas symbolic AI can easily incorporate domain knowledge because the knowledge is explicitly represented, usually in the form of some kind of logic language. They have very good systematic generalization and compositionality, and they are, by design, human readable and explainable because we can construct chain of thought reasoning on why we achieved a certain outcome. On the other hand, statistical AI, symbolic AI requires to build a complete picture of the knowledge of a certain domain and has difficulties in handling in partial, inconsistent knowledge and exceptions, which has proven way too brittle for solving perceptual tasks. There have been some attempts in the 80s or the 90s, but eventually for everything that involves perception, which is a huge part of AI nowadays, symbolic AI by itself has proven to be too brittle. We also have problem with knowledge acquisition. Building a knowledge graph is a huge endeavor. The knowledge acquiring expert or common sense knowledge is a bottleneck. Whereas on the other hand, statistical AI can learn directly from examples and labels, which are a form of knowledge, but are much easier to acquire and much cheaper to acquire. And we can build in some robustness to imperfect knowledge, which is usually derived by having some noise in the labels. Symbolic AI is expensive. Reasoning is computationally very expensive. Whereas on the other hand, statistical AI, machine learning, is based on some simple core algorithms, which are highly scalable and very good at representation learning. With their recent advances on computational power, this scalability has really been proven effective. So the goal of merging these two paradigms is the ability to incorporate the strengths from both approaches. So what could we do if we had systems that can learn directly from examples, which are cheaper to acquire, but can also incorporate domain knowledge, explicit domain knowledge representation? What could we achieve if we had systems that can learn, that can generalize well within domain, but also exhibit good systematic generalization and compositionality? What can we achieve if we combine the scalability of machine learning with the ability to generate systems that are intrinsically and by design explainable? This concept is not new. For example, in the 1990s already, Marvin Minsky suggested the idea that these two paradigms didn't really have to compete, but could cooperate to achieve a more intelligent computational system. Today, we have a plethora of approaches that fall within the neuro-symbolic AI paradigm, from using neural networks to compensate the issues with knowledge acquisition and solving the acquisition bottleneck, or performing approximate reasons, all the way to building neural networks based on some form of differentiable logic, and use that to integrate domain knowledge into the neural network. Within these variety of approaches, there have been a few attempts to understand, to build a taxonomy of systems. One is the Kautz taxonomy, which was introduced by Henry Kautz in the IEEE Engelmore Memorial Lecture in 2022. The other one is the boxology paradigm introduced by Frank van Harmelen at University of Amsterdam. The taxonomy by Kautz has the advantage of being more synthetic, whereas the boxology, I think, is more principled, but requires a lot more time to explain. So I will use this as a guide to understand what we mean by hybrid system. Kautz defined 6 possible designs encompassing both a current system, which he denotes as symbolic, neuro-symbolic, to future systems, which we don't really have right now, that are inspired by the concept of a dual system, thinking system 1 and system 2 thinking as theorized by Daniel Kahneman. In between, we have a variety of systems that use a combination of techniques from the machine learning and the symbolic domain as coroutines. We will see a couple of examples in the computer vision domain of systems that fall under the neuro-symbolic paradigm. And more recently, systems have emerged in which we can achieve a tighter integration between the 2 paradigms, which are denoted in Kautz autonomy as neuro-symbolic. In these systems, symbolic rules are used as templates to generate structures within a neural network that can have a dual interpretation, can be seen as neural networks and then can be trained as neural network using stochastic gradient descent, but it can also be seen as a some form of logic language and can be reinterpreted or mapped to a symbolic state. Within this family of approaches, we have there are a number of techniques that have been proposed. I will talk mostly about logic tensor networks, which were proposed by Serafini and Villa-Garces in 2016. But we also have neural probabilistics of logic. We have a type of logic proposed by IBM. So we really have a number of different and at the moment competing approaches. What we have demonstrated is the ability to encode different types of relationships and the ability to learn from data and prior symbolic knowledge by jointly performing training and inference on both systems at the same time, which I think is what really differentiated this paradigm with respect to previous attempts. Moving from this introduction, let's see what has been done in computer vision with this particular paradigm. There are essentially 3 goals that the computer vision community seeks to achieve from neurosymbolic integration. The first goal is interpretability. Neural network, especially convolutional neural network, are quite interpretable, but still they are not really interpretable by design models. I will not talk a lot about interpretability today, but I think this is one direction where the computer vision community would really like to go. The second principle is be able to perform knowledge-informed machine learning from data and knowledge. If we can complement the information from data with prior knowledge, we have been able to learn in a more efficient and more robust way from noisy and limited samples. We will see some applications related to zero-shot learning. We can do different form of semi-supervised learning, and these systems have been shown to be more robust to adversarial examples, to be able to learn under logical constraints, and I will show some examples of how we can achieve those in different settings. The third goal is being able to integrate perception and reasoning. Many computer vision tasks especially if we move from simple classification to more complex tasks, such as visual query and answering, require some form of inductive and deductive reasoning. The ability to reason can also improve, in principle, generalization to unseen domains. Let's see with an example. One of the tasks in which Neuro-Symbolic AI has been more effective are more complex tasks, such as visual query and answering or event detection. In visual query and answering, we are given an image and we are given a question that we need to answer. And in many benchmarks, this question requires some form of understanding of the scene and some form of deduction or inference on the scene. For example, in this case, we are asked to count how many cubes are behind the cylinder and how many of these cubes are large. So the system needs to understand what is a cube and what is a cylinder and count how many objects we have. Several approaches for visual query and answering rely on a cascade from a neural network into a symbolic reasoner. So the neural network solves the perceptual tasks and derives a structural scene representation on which we can then execute a symbolic program. Similar approaches have been tried in event detection. For example, in this system, we are performing event detection in soccer games, starting from videos. In this case, the deep learning-based system solves the perceptual task, whereas the logic system defines, detects, and concatenates events according to the rules of the games. In games, we have a lot of prior knowledge in the form of rules. For example, we can define that the pass is a series of events in which first we kick the ball, and then we shift the ball possession from one player to another. With this kind of system, however, we have a couple of issues. The first issue is that the two components do not really talk with each other. So the information from the event detection systems cannot be backtracked to the perceptual task. The other problem is that the event detection system works purely at the symbolic level and cannot really integrate visual information in order to facilitate object detection, event detection. So we are able to detect certain type of events, but not other, which requires some form of a more fine-grained visual representation. So to solve this integration, enters Neuro-Symbolic, especially Logic Tensor Networks. This is a computational framework which is based on a differentiable first-order language, which is interpreted in a fuzzy way, meaning that a statement can be not only true or false, but can have any level of truthiness in between. This first-order language is grounded into components that are trainable. Usually, symbols are grounded depending on their nature. So object instances, for example, this image is typically grounded by continuous embedding. And this, if you're working in machine learning, the concept of embedding is probably absolutely not new to you. Predicates are grounded by parameterized components, which compute the truth value of the corresponding predicate. For example, the predicate zebra computes the probability that this image contains a zebra. And typically, predicates are grounded by a trainable component, which is a subpart of the more complex neural network. So in this case, a simple MLP. Based on these symbols, we can construct the theory, a knowledge base. This theory encodes what we know about the problem that we want to model. It will encode, for example, known facts, the fact that this specific image does contain a zebra. It will encode some background knowledge, for example, the fact that the zebra has stripes. It can encode the logical constraints, for example, the fact that if an animal is a zebra, it cannot be a horse or it cannot be a bear. This theory is a template because we don't really know whether the theory is true or not. The theory is based on a parameterized system, which will need to be trained to compute the knowledge base. This training is achieved by substituting empirical risk minimization, which is our current framework, with the concept of training by best satisfiability. All the predicates are combined using fuzzy logic operators. So our entire theory is grounded by a neural network with unknown weights. And we want to find the set of weights which maximize the satisfiability of a knowledge base. The knowledge base might not be satisfiable in the classical sense. So there isn't probably a set of weights which completely satisfies all the axioms. There could be contradictions. So the neural network will try to find the best combination of weights that satisfies most of our theory. These systems allows us to construct this neuro-symbolic duality in which a neural network can be seen as a set of functions that compute that are grounded within the 0-1 range, or a set of axioms. For example, this neural network can be reinterpreted as the truth value of this statement. If Mario is born in Turin, then Mario is also Italian. Notice that not only predicates, but also logical connectives and quantifiers must be grounded in order for the entire system to be differentiable and be trained with using neuro-symbolic, using statistical stochastic gradient descent. The choice of grounding is critical. I will not have time to go into these details, but there is still a lot of work to be done in order to make this grounding really stable and trainable with good gradients and good numerical properties under complex systems. With this, we can solve this integration. The promise of this system is to be able to build a cycle in which we can switch back and forth. So we can introduce transfer knowledge from the symbolic space to the sub-symbolic space and back. Most of my work has been on knowledge transfer, but the goal, the vision is to build systems that can do both and can learn and reason at both levels. So we can train the neural network with efficient algorithms, but we can also reason at the conceptual level, and we can speak with users and external knowledge bases using a language that they can understand. For the sake of clarity, I will show just a couple of examples of how this system can work. And then, of course, if we want to, we can go back to other type of examples. The first system that we have built using this concept is Faster LTN, which is a version of a well-known Faster RCNN object detector, in which the RPN, the region proposal network, computes a first proposal for the objects. And then at training time, we refine the predictions by incorporating mereological constraint in the form of part of relationships that we derive from an existing knowledge base. So for example, the fact that a cat is composed by a tail, a head, and an eye, and the system must learn to predict bounding boxes classifications using this information, so that the predictions are not only consistent with the examples, but are also consistent with the knowledge base. Another problem in which we have been working a lot is that of zero-shot image classification. In zero-shot learning, we have a few classes which are seen at training time. And at test time, we need to be able to recognize also examples from previously unseen classes. For example, at train time, we might see a zebra, but at test time, we also need to differentiate between a zebra and a tiger. At training time, of course, we need to compensate this lack of examples with some sort of information regarding the data, the animals in this case that we want to recognize. And this this knowledge comes in the form of attributes. So we have an attribute matrix which gives us information about which properties are expressed by which animal. And we use this information to build a fuzzy logic visual network in which the images are embedded using some trainable embeddings. And the predicates are computed by a distance in the embedding space between some prototypes, which are derived from the attributes and the embeddings of the image. The concept again is the same. We train by maximizing the satisfiability of a knowledge base. And in this case, the knowledge base comes with different properties, different axioms which encode different knowledge that we have about the system. The first axiom encodes what we know about labeled examples. So the first axiom replicates empirical risk minimization, essentially. The second axiom encodes encyclopedic knowledge about the class hierarchy. So if an image belongs to a certain class, it might also belong to the corresponding macro class. The third axioms encode some properties about the feature representation. Images from the same class should have similar representations, and this is akin to a form of contrastive learning. The fourth axioms encode the possibility of learning from exceptions. Even though we are given attributes at the class level, we know that we have exceptions. We know that there are some examples within our set of examples that do not have all the attributes that are associated with that class. Typically, among the attributes, we have, for example, information about the color or information about certain part of the animal. So, for example, we know that a zebra has stripes. We know that a zebra can run, and we know that a zebra has a tail. Most images will express the attribute that the zebra has stripes, but many will not show the zebra running. So not all the images will express that particular property. And we encode these by explicitly telling the network that for all classes, it must expect to have some exceptions, some classes, some examples which do not show the property of the corresponding class. And I think this is particularly interesting because it gives us the ability to state properties that are valid not only at the individual example, but also at the group level. By the way, it also breaks the EED assumption. So we do not necessarily have to assume that all examples are identically distributed, but we can encode differences between different groups of samples. And of course, we have shown that this system outperforms the competitors, but I don't really think that is particularly of interest, maybe in this context. What was particularly interesting to see is that this system achieved comparable result with systems that are significantly more complex, even in terms of architecture, like, for example, attention-based methods, or in terms of training. So for example, generative methods will try to synthesize examples from the unseen classes. We don't need to do that. We can simply exploit knowledge, conceptual knowledge about the unseen classes. So we don't necessarily need to have examples or to synthesize them using a generative technique, but we can exploit information that is available from knowledge bases such as WordNet or ConceptNet or any other knowledge base that is available. So for the interest of time, I will skip scene graph generation, but I can go back to it if people are interested. And I will go directly to Visual Sudoku, which is another benchmark that is particularly interesting. In Visual Sudoku, we are given a set of images of handwritten Sudoku boards, and we need to decide whether the board is the correct solution or not. So in this case, I think the solution is correct. The solution is correct if we have no repeating numbers in each row and each column and each subblock of the Sudoku board. Our goal is not really to solve the Sudoku problem, but our goal is to learn to recognize digits without being given any labels about the digits. All the information we have is whether the Sudoku board is correct or not. And we want to predict, at the same time, recognize the digits, but also predict whether the solution is correct or not. A CNN cannot be trained to solve its task. We tried, but it will not be able to learn. The accuracy will be essentially random. Whereas in the Logic Tensor Network, we can use this template to encode inside the neural network the rules of Sudoku. So we can say that for each sub-element, so for example, for each pair of digits that appear in the same row, they must have different numbers. And if they have different numbers, the solution is correct. If they do not have different numbers, the solution is wrong. And with this information, we are capable of achieving very good discrimination at the board level, but we're also able to learn the digit classification quite correctly. Notice that in this case, we are not given any label whatsoever apart from the information that the board is correct or not. Most of the learning comes from solving the logical constraint. So in this particular example, the logical constraint is even more important than the label themselves. So I think that with these few examples, there could be many more. I've been able to give you a glimpse that prior knowledge can be beneficial, especially when supervision is scarce, noisy, or incomplete. But at the state of the art, it requires to design an ad hoc network. So I think this is really one of the bottlenecks in applying Neuro-Symbolic AI at scale. We still have to prove the ability to scale to very large data sets. Most of the benchmarks that we have used so far are relatively small compared to the state of the art. We need to write the knowledge base. We can integrate some external information, but most of our knowledge bases so far have required a lot of manual tuning. I've managed to talk for 30 minutes without mentioning large language models, but of course, at this state of the art, we need to understand how language models fit in this picture, whether we are a competing paradigm or whether Neuro-Symbolic AI can also incorporate language models. And we need to really close the Neuro-Symbolic cycle. So in the system that I've shown you, we are able to perform knowledge induction, so we can induce knowledge inside the neural network, but we cannot have a neural network learn new concepts and integrate those new concepts back at the symbolic level. And this is something that we really want to do. So our vision is that of the system where we can train the network by providing examples, by checking the knowledge, by providing new knowledge, by checking and verifying the knowledge that the neural network has learned and modifying it on the fly. We are also exploring different tasks. We are investigating some applications in the medical field. In general, I think that this paradigm is well suited for industrial problems where usually we don't have that much data, but we do have a lot of information about the setting and about the process that generated the data. And we're also looking at sociocultural interpretation of images, especially how we can integrate common sense knowledge, and how can we exploit this paradigm to take into account cultural preferences in interpreting images in this case. Before wrapping up, I really want to thank my collaborators, especially my PhD students, Francesco Manigrasso, Luca Piano, and Alessandro Russo, because of course, we do the talk, but someone must also do the hard work of putting these systems together. And I would also like to thank the Smart Data Center at Politecnico di Torino for the financial support. The Fair Future and Artificial Intelligence Resource Foundation and the i4Media Consortium for financial support for this research. I hope that the talk was interesting to you, and if you are interested into these topics, we also have quite a tridy community. There is a the Conference on Neuro-Symbolic Learning and Reasoning that this year will happen in Barcelona in September. Since last year, we also have a Neuro-Symbolic Artificial Intelligence Journal. And if you're interested, there is also a Neuro-Symbolic Community Slack, which you could join. If you want to know more, just feel free to drop me an email also at the end of this talk. So thank you very much for your patience, and I hope that the talk will elicit some questions.
Yep, thank you very much. So for all attendees online, there is a Q&A function, but you can also raise your hand as Michael did. And then I can allow you to talk. Okay, Michael, please.
Can you hear me?
Yes.
Yes.
Right. Cool. I'm sure we've met before, given the Neuro-Symbolic setting. So I was wondering, these logic-based techniques or symbolic-based techniques, we claim that they're reliable and have good generalization and so forth, but usually over very sort of compact subdomains or very straightforward things like class inclusion constraints. So what do you think the prospects are for, given how simple those things we are actually able to incorporate tend to be? What do you think the prospects for something like a language model actually producing those constraints and feeding them into the system, to the extent that they're, and doing that in an end-to-end way? That seems like it would be very fun to try and might well work.
Yes, you're absolutely right. One of the things that we're looking into is how we can generate new axioms and new knowledge to be included in the knowledge base. So solving this manual, so we envision a system in which the knowledge base does not really need a lot of tuning. And large language model could absolutely be a way of achieving this goal, given that they are very good at approximate inference. Of course, they approximate knowledge retrieval. So I think there are a lot of people that are already working on that. And I expect to see also probably some work at the NeSy conference this year on this topic. I also think that in this context, hallucinations, which could be a problem in other context, might not necessarily be that problematic, because when we then train the logic tensor network, if there are facts, axioms which contradict information coming from the examples, this system can disregard those, in principle, can disregard those axioms which are not correct. So even if the language model should hallucinate some of the logical constraints, in principle, the network should be able to disregard that automatically. So I think that's a very interesting direction to go.
It's also great to see these logic tensor networks. I was completely fascinated by Politecnico's tensor product networks back when I was in grad school in 1990. And it's great to see this coming back. And one last comment, we do quite a lot of work in my lab on trying to improve the reasoning reliability of large language models. And it strikes me that this sort of setting, where you've got an end-to-end setting, where logical representations are actually used, might be useful for providing that sort of training constraint for getting better logical reasoning more widely. So I'd love to follow up and talk about possible collaboration.
Absolutely, absolutely. That would be great. We have been working on a system to use logic tensor network as a probe. This work has been as a probe to understand, as an explainability tool for language model, but I think that integrating them at training time or even at inference time, because in these examples, we have been using LTNs mostly at training time to generate essentially to complement the loss with a semantic component. But nothing prevents them from being used also at inference time to perform some sort of approximate reasoning. And this has not really been a focus of my work, but if you look at the Logic Tensor Network paper that was published by Sami Badreddin and colleagues a couple of years ago, you will see also examples of how to use LTNs for approximate reasoning, and that could also be integrated at inference time. And that is certainly something that we would like to explore.
Fantastic. Very nice talk.
Thank you.
Thank you, Michael. Lia, can you see the Q&A function in
Yes,
Zoom?
I see 2 questions/comments by Kimin Bao. I think NeSy can be seen as a good component for LLMs in addressing complex logical reason. That's certainly true. Prompt augmentation, that is also something very interesting. There is a lot of work that has been done on using some form of retrieval augmented generations, in which you can, and of course, retrieval augmented generation does require some sort of knowledge graph or knowledge base. So that is certainly an area of direction. I think there are some fundamental differences between LTNs and similar systems and, for example, knowledge graph embeddings. There has been a recent talk by Frank van Harmelen that is available online. It's part of the webinar series of the Neuro-Symbolic AI journal on which properties, which semantic properties are preserved when we move from the original knowledge graph to an embedding space, and what are the potential issues related to that, because the embedding space is geometrical and therefore does not necessarily preserve the semantics of the original knowledge graphs. But that is certainly an area of interest. The second question is, what is your opinion of the current state of computer vision with NeSy? We have seen great success in natural language processing through self-supervised training, such as LLMs. However, this does not seem to have happened yet in computer vision. What is your opinion on integrating NeSy with computer vision or even multimodality area? I'm not necessarily sure that there hasn't been a lot of progress in self-supervised training in vision. There has been a lot of work in integrating self-supervised training in vision. Multimodality, in multimodality, however, it appears that visual understanding might still be an issue with current multimodal large models. I think that NeSy can help in two ways, but still needs to be substantially improved. The main, where I see the main opportunity is related to what could be perceived as the role of symbol in multimodal learning. In the examples that I have shown you so far, symbols are really mapped to one representation, but nothing prevents them from being mapped to more representations. So the same symbol could be associated, for example, with a textual embedding, could be associated with a visual embedding, could be associated with the smell, could be associated with the sound. And in principle, I think that this symbolic reasoning, the symbolic component could help bridge the different modalities without necessarily requiring the embedding space to be aligned or to be geometrically compatible. Self-supervised training is not necessarily an alternative to Neuro-Symbolic. In fact, we can use all the tools that we have in standard machine learning, since we are training with stochastic gradient descent. We can incorporate self-supervised training inside also the NeSy paradigm. One way we could do that is specifically geared towards Neuro-Symbolic integration is by using consistent with prior knowledge to enforce training on unlabeled samples. There are a few works by my group, but also by Sami Badrin at Sony AI, by Luciano Serafini at Bruno Kessler Foundation in Italy, in which most of the training data was not labeled. And the training supervision comes mostly from the prior knowledge and from satisfying the prior knowledge. We have another, if that is okay with you, I will go on with the online questions, but of course, if there are also questions in person, please do let me know.
Yeah, let's maybe see if there is a question here from the people in the seminar room.
I have a question.
Sure.
You talked about adversarial attacks and
yes,
Neuro-Symbolic models being more robust to adversarial attacks, which I can really believe, but do you have an overview of the area of what kind of research is out there?
The main paper that I know of has been published by the University of Siena. It is in this case, the task was a standard computer vision task, so they experimented on standard classification, multi-class and single class classification. The main potential for integrating domain knowledge comes at training time. So at training time, the system is trained with standard supervision constrained by domain knowledge. This has shown to be a little bit more robust than training under supervision only, but I think it depends a lot on the tasks, because it depends on whether the domain knowledge can help you build more robust features. In some cases, the supervision provided by the label is sufficient to learn robust features. In other cases, it is not. So it is really, I think, problem dependent. The second approach, which I think could be more interesting, is to use domain knowledge at inference time to build some projection criteria. So in this case, they evaluated the average satisfaction of a domain knowledge in distribution data, so for real data, and they built a projection criteria. Since many adversarial examples, although they maintain the same class by definition, they might not satisfy the domain knowledge as well as the original samples. And with these, they were able to achieve better performances on the tests they tested. In this case, animals, I think it's animals with attributes, Cypher 100 and Pascal part, which is an object detection and part of benchmark. I'm not sure there have been many other works on this topic. I think this is the one I know off the top of my head, but I can reach out to them. One of the authors is working at my institution, so if you're interested, I can put you in contact. And
yeah, that would be great. Thank you very much. Also, thank you for your talk. It was really good.
Thank you. Thank you.
More questions? I guess my question is kind of similar with what Michael was talking about for generating knowledge graphs using large language models.
Mm-hmm.
And I guess my question is more about the human-based generation of these knowledge bases. How do you rank your the axioms that you're using in terms of like utility, or like the eats fish one for computer vision seems a little silly or like strange to me that would be one in there, because it's not likely that the picture is going to have them eating or having something eating fish potentially. And I guess like if you look around the room in terms of scalability, like how many axioms would you need to be able to identify in the space you're in right now to identify the things around you? Is that something that a large language model could help with, or is it something like kind of out of scope of the project?
I think that there are essentially two types of knowledge that we can embed using this type of two types of constraints. One is related to encyclopedic knowledge. So, for example, to give you an example, in the case of part of, if we need to predict whether an object has a certain class or is part of another object, we have a lot of information about the part of world relationships. That kind of encyclopedic information is very expensive to generate. Fortunately for us, there are a few good resources already out there. For example, WordNet, ConceptNet, but still this is the bottleneck, and this is an area where large language models have been proven successful. There are already a few works. Off the top of my head, I can think, for example, of Comet, which was one of the earliest work in which a large language model was was used to complete the knowledge base. So that is certainly an area where the knowledge acquisition bottleneck is really an issue, and large language model can certainly help. The other type of axioms, and I think this is an area where we could solve the problem without the help of language model, are axioms that encode high-level inductive biases. Usually in computer vision, we incorporate inductive biases as part of the architecture. For example, convolutional neural network assume that the object is composed, that objects are composed of smaller parts, and that these smaller parts are local and are insensitive to translation. We incorporate inductive biases by using data augmentation, which, however, is very effective and very simple to do, which is why everybody is doing it, but it is also very expensive. So I think that one way these techniques could help is by designing, crafting some higher level inductive biases that do not necessarily are not necessarily concerned with the local properties of the image, but are more concerned with the type of reasoning that we have to do in order to solve the images. So, for example, the fact that there are exceptions could be really useful. We are working on a new version of FLVN that will be hopefully published or at least in preprint relatively soon, in which we are trying to investigate what is the role of such higher level inductive biases versus the encyclopedic knowledge. Where do the benefit actually comes from? And at least for a FLPN, we saw that incorporating the class hierarchy is useful, but only to a certain extent, because the embedding are somewhat hierarchical already. So a lot of information about the class hierarchy is already captured by the embedding space, at least with ImageNet pre-training. However, for example, accounting for exceptions was really useful, because one of the problems with zero-shot learning is that it tends to overfit to sync classes. So it learns very well how to classify examples from classes that were seen at training time, but has really difficulty disentangling the visual property of the attributes from the visual properties of the class. And that is something where, on the other hand, the axioms have been really useful. So not necessarily encyclopedic knowledge is going to be the only benefit of designing this system. I think the holy grail is finding those higher level inductive biases that can be used across different tasks and different domains, and really improve the robustness overall of the system.
Thanks.
Thank you. Very nice question.
Great answer. Thanks for, yeah, I wish I was working on what you're working on. It's pretty exciting.
Having a look at the time, maybe the last question back to online. So
okay.
Shane wrote about neuro-symbolic reasoning and has a question about ideas for language or image knowledge decomposition, but I can also unmute if you would like to
yes,
talk.
maybe.
Hi, hello. So currently I'm doing the neuro-symbolic, the topic to solving the multimodality problems. So I just doing something about language decomposition or image decomposition. I have known the image decomposition is like the concept grounded the knowledge attribution, knowledge object information. So if I want to decomposition my language to a concept, some element, then I can combine the concept to solving the just like the VQA problem. So do you have some idea, or do you know some works is about the language concept, the decomposition? Then we can use the knowledge from maybe from the large language model, or from the some other data set, or from the distillation. So I just want to know the some ideas. It's about the language concept decomposition. So
Thank you. Thank you very much. Excellent question. I think that grounding concepts in images has been one of the longest challenges in computer vision. So how can we extract concepts, map concepts into images? There are several works that have been done at least in computer in image interpretation on trying to force the network to learn features that are mapped to human interpretable concepts. I'm thinking about, for example, concept bottleneck networks, many other works in the area. Also, one of my colleagues, Gabriele Ciravegna, from another group at my university, has also worked extensively on this topic. The main difficulty until recently was to achieve concept alignment without losing accuracy, because one of the main challenges is that if you build a system that in which the features learned by the neural network are aligned with the human interpretable concepts, often you lose some classification accuracy. And at the end of the day, I think that in practical problems, users do care about explainability, but at the end of the day, they also care more about performance. So even though we claim that explainability is important, in practice, I see very few people are willing to trade off accuracy for interpretability. But I think that is a very excellent question, and certainly one of the areas where we would like to work, because concepts that decomposing the image into a series of concepts would allow you to close the neuro-symbolic cycle. So that's an area. In computer vision, there are many techniques that have been developed to learn these interpretable concepts. Of course, it is easier to do when the domain is relatively small. So it is more difficult to do it in an open-ended way. The other direction we could go are foundational models. So how can we integrate foundational models in these cycles? And for that, we might be able to solve the grounding or even of complex or abstract concepts. For example, in the medical domain, we have been working for a few months now on applying these techniques to the medical domain, and that is an area where the word is essentially, you can assume a closed word, because the human body has only so many parts, and the number of diseases that we can get are fortunately not unlimited. So it is easier to build these type of systems, which if you can assume that the domain knowledge is somehow limited. And then in that case, also concept decomposition can be more easily achieved, I think.
Okay, thanks.
Okay, great. Thank you very much. Thanks for this really interesting discussion also after the talk. Before I end the seminar for today, short announcement. The next one is in 3 weeks, tomorrow in 3 weeks, on 20th of June, this time at 1 p.m. Nikola Kazabov will join us here in person. He is from the Auckland University of Technology, and he will talk about mathematics and brain-inspired neurocomputation in AI. So invites will come soon. So let's thank Lia again for a very exciting talk and super discussion.
Thank you. Thank you very much for the invitation. It was really a pleasure and a great honor to be virtually there with you today. Hopefully one day I might even come in person.
You should absolutely.
But it's a long flight.
Okay, so have a great day in Italy, and to all the others, have a great evening, and see you soon.